Hi everyone. Before we begin, let me remind you that the exercise for Unit 2 is due on Monday, April the 20th. Okay, so please try to finish your grammar. If you have any question, email me, and when you are done, create a PDF file and upload it to the virtual campus. Okay. Um, Today we are going to focus on a problem that at first may seem related to the kind of situation and algorithm that we studied in the previous lecture. Okay, remember that we have solved the Königsberg's bridge problem in general. When we are given a graph, now we know whether there is a path that uses all the edges once and only once, and the solution was quite easy. We only needed to uh, count the number of vertices that are the edges that are incident in each of the vertices. Then we have the degree, and if the number of vertices with odd degree is 0 or 2, then we know that there is an Eulerian path in the graph. Okay. And now we are going to consider something that, as I've told you, may seem similar. Okay, so now we are interested in what we call Hamiltonian paths. Hamiltonian paths are paths that use all the vertices in the graph once and only once. Okay, so for instance, here in the figure in the slide, you see a graph that comes from a geometrical figure, from a polyhedron, and you can see that we can make a path in the graph that uses all the vertices once and only once, and in fact it starts and ends in the same place, so it's a cycle. Okay, this is what we call a Hamiltonian circuit or a Hamiltonian cycle. In general, if we have a path that uses all the vertices once and only once, then we call that a Hamiltonian path. So you may think that this might be similar to the problem of finding a path that uses all the edges once and only once. But the situation is much more complicated. Let me give you an aside of what kind of problem is this and what is the relationship with the problem that we have studied and the differences. Okay, so let me please tell you first of the situation here with a graph. So imagine that we have a graph with, I don't know, 10 vertices. Okay, so if we are given a certain list of the vertices of this graph, for instance, I don't know, 7, 3, 4, 5, 6, 4, 6, 5, 2, 8, 1, 9, and 10, then we can easily check whether this is a Hamiltonian path or not. Okay, so we are given this, and we are asked whether this is a Hamiltonian path or not. What can we do in order to check this? Well, what we can do is to go to the graph or go to the adjacency matrix and see if indeed we have an edge from 7 to 3. Also, if we have an edge from 3 to 4. Also, if we have an edge from 4 to 6, and so on. Okay, we can also check, in this case it's trivial, that all the vertices appear in the list once and only once. Okay, so in general, if we are given a list of vertices, it is very easy, it is fast to check whether that list is Hamiltonian path in the graph. okay? But if you are given the graph and you are asked to find a Hamiltonian path, then it's not so clear what to do. Okay, so in general, you can try to start with a vertex and use an edge that comes out of that vertex, go to another vertex, but it's not so clear what to do. Okay, and in general, there is no algorithm, we do not know of any algorithm that is best than trying all the different possibilities. Okay, so we start from a vertex and we try to go to a different vertex, and from that to a different one, and we check whether we can use all the vertices once and only once. Okay, so this is an example of a kind of problem that we call MP. This is a problem that can be easily checked. Okay, if we are given a proposed solution, um, then it is easy to check whether it is indeed a solution or not. So if we are given a list of vertices, it is easy to check whether uh, the list is indeed a Hamiltonian path or not. Okay. There is also a different type of problems. For instance, here, Hamiltonian paths. There is another kind of problems, for instance, checking whether there is an Eulerian path in a graph, which are easy to find. Okay, their solutions are easy to find. Okay, and the name P and NP comes from P is polynomial time. These are problems that can be solved. Their solutions can be found with an algorithm in a time that is grows as a polynomial in the size of the input, while NP are problems that can be solved in polynomial time, but in a non-deterministic machine. Okay, so if we are able to explore all the possibilities, then with a non-deterministic machine, we can solve the problem in polynomial time. But we need the possibility of being in more than one solution at a given time, to explore many solutions at a given time. And that is not a realistic computer. That is just a model of a machine that it's useful to study some problems, but is not a real machine. Okay, so it's similar to what we did in the first unit when we had non-deterministic finite automata, and we use them to define different languages, but then we needed to transform them into deterministic finite automata in order to be able to use them in real computations. Okay, so the situation here is more or less the same. We have P, which are those problems that we can solve in polynomial time in an efficient way, in a fast way. And then we have those problems that we can solve in a fast way, but only if we have a non-deterministic machine. Okay, so it can be seen that this is equivalent to having a way of easily checking whether the solution is correct or not. Okay, you can think of this as having only the branch of the tree of the non-deterministic machine that actually solves the problem. If I give you only that branch, then you can check that the solution is correct. But in general, in order to find that branch, you may need to explore all the different branches in the computation tree. Okay, so one of the most important questions in mathematics, and in particular in theoretical computer science, is whether NP is equal to P. We have already talked a little bit about this problem, and I want you to remember that there is a $1 million prize for the person that solves this problem. Okay, so we strongly suspect that P is not equal to NP. They are different. It's not the same to be able to check quickly a solution than being able to find that solution. Okay, but we have not proof of that. Okay, we have a strong um, evidence of this fact, but we have no mathematical proof. Okay, it seems logical. It seems that it's not the same to find a solution than to check a solution that you are given. It seems that obviously it's easier to check the solution than to find it, but we have no proof of that. Okay, and in order to investigate this kind of relationship between P and MP, a certain number of problems have been identified that are important for solving this question. And these are the problems that we call NP complete. So these are problems that are in NP, and they are such that any other problem in NP can be reduced to a problem, to this problem, in order to solve it. Okay, so the idea is that a problem is NP complete if it is in NP, and any other problem in NP can be solved quickly if we knew, or if we know how to solve. So let me call A is NP complete, how to solve A quickly. Okay, so in a way, NP complete problems are the most difficult among the NP problems. Okay, so they are problems that can be easily checked, but if we knew how to solve these problems quickly, then we could also solve quickly any other problem in NP. Okay, we don't know whether we can solve them quickly or not, but if we could solve them quickly, then any other problem could be solved quickly. And it happens that there are many natural problems and important problems that are NP complete. They are difficult, but they are natural. They appear in many different situations. Okay, and in fact, finding out if there is a Hamiltonian path in a graph is NP complete. Okay, so it turns out that this problem is very difficult. This problem of finding or knowing whether a graph has a Hamiltonian path or not is very, very difficult. Okay, we don't know how to solve it quickly. And if we knew how to solve it quickly, we could be able to solve many other problems quickly, and we will also win the $1 million prize, because then we could show that P is equal to NP. So we strongly believe that this is not the case, that P is not equal to NP. So we strongly believe that there is no algorithm that can solve this problem quickly. So what I want you to remember of all this is that this kind of problem, NP-complete problems, the Hamiltonian path problem, is a problem that we strongly suspect that is not possible to be solved quickly. Because if we could be able to solve this problem quickly, then we could solve many other problems also quickly, and we strongly suspect that there is no quick solution for those problems. Okay, so it turns out that the problem of finding or checking whether a graph has a Hamiltonian path or not is very different from the problem of finding whether a graph has an Eulerian path or not. Because in the case of Eulerian paths, we have an algorithm that is quick in order to check whether there exists such a path or not. We only need to compute the degrees of the graph. And we do not have anything like that for Hamiltonian paths. And we strongly suspect that there is no such an algorithm. It's not that we have not been able to find it, but that there is no such an algorithm. Okay, so then what can we do with the problem of Hamiltonian paths? Well, we can do several things. We can try to solve it by brute force. We can try to enumerate all the different paths and try to find if any of the paths is a Hamiltonian path, if any of the paths uses the vertices in the graph once and only once. And this can work for small graphs. If the graph is small, well, we can try to enumerate all the different paths and check if any of them is a Hamiltonian path. But if the graph is bigger, if the graph has, for instance, I don't know, 2,000 vertices, then this is almost impossible. Okay. We can also try to find approximate solutions. Try to see if we have a path that is close to a Hamiltonian path. Okay, and that can work out in several situations. Okay, or we can try, and this is what we are going to do here, to study Hamiltonian paths not in all graphs, but just in a family of graphs. Okay, so if we restrict ourselves to families of graphs, then maybe the problem might be easier to solve than in the general case. So the result that finding a Hamiltonian path or finding out if a graph has a Hamiltonian path is NP complete is for all graphs. If I'm given a graph that is any kind of graph. But if I restrict the input to families of graphs, then the situation can be easier. Okay, exactly what happens with a family of graphs that we have already studied. Remember that we have studied what we call tournaments, which are directed complete graphs, and in these graphs we can show, in fact we are going to develop an algorithm for this case, we can show that there is always a Hamiltonian path. For instance, in the graph of the figure, you can check that if we start in 1, we go to 2, then we go to 4, then we go to 6, then we go to 3, and finally we go to 5, then we have a Hamiltonian path, a path that uses all the vertices once and only once. Okay, so in this particular case, we have an algorithm, also a quick algorithm, that is able to check whether the graph the graph has a Hamiltonian path, and in fact to find the Hamiltonian path. Okay, but we need to impose that the graph is a Hamiltonian, is a tournament. It does not work for other kinds of graphs. Okay, so what is this algorithm? Let me explain what the algorithm is, and then we give some examples. Okay, so the algorithm is quite easy. It's surprisingly easy. What we do is first we check that the graph is a tournament. If it is not a tournament, then we cannot apply the algorithm, or we can apply the algorithm, but it is not guaranteed that we will find a Hamiltonian path even if it exists in the graph. Okay, so it's an algorithm that works for Hamiltonian for tournaments, and in other cases it may not work. Okay, so the first thing is to check that the graph is a tournament. Once that we know that the graph is a tournament, then we write down all the vertices in the graph in some order, in the order that you want. It doesn't matter, okay? So this is similar to what we had in the previous lecture, in which we had to select an initial vertex in order to find the Eulerian path in the graph, and this choice of vertex could influence the kind of path that we find, but it will always succeed no matter what is the vertex that we choose. So it doesn't matter which order of the vertices we choose here, we will always succeed. Maybe we find a different Hamiltonian path, but we will always succeed. Okay, so we choose an order. If we have 4 vertices, then we can choose, for instance, 1, 2, 3, 4, 4, 3, 2, 1, 1, 3, 2, 4, whatever we want. Okay, we choose an order. And then we want to, we are going to try to insert the vertices in the path in that order in the first possible position. Okay, so we take the next vertex in the list, and we are going to write a path in which we insert each of these vertices in turn. And we try to insert it in the first possible position depending on the vertices that we have already included in the path. Okay? And we will see that we have 3 different possibilities. The first is that the the next vertex can be added at the very beginning of the path. Okay? If it cannot be added at the beginning, then maybe it can be added in the middle. And if not, then it will be inserted at the end. Okay? So what we do is to try to insert it as soon as possible, in the first position that it is possible. And here we see the idea. We see graphically what this algorithm is doing. So imagine that we already have this path in the graph. We have already inserted these vertices u1, u2, up to uk. And now we need to insert v. V is the next vertex in the list, is the next vertex to be inserted. Okay? So in this situation, we try first to insert the vertex at the beginning. If we have an arrow from V to U1, the first vertex in the path, then we insert it there. Okay? If we have that, then we insert it there. But maybe we do not have that arrow from V to U1. Now is when we use that the graph is a tournament. It's a complete directed graph. So if we can not go from V to U1, then it means that we can go from U1 to V, because the graph is complete. So if we do not have an arrow from V to U1, then we must have an arrow from U1 to V. If we do not have that arrow, then the graph is not complete and we cannot apply this algorithm. So if we do not have the arrow from V to U1, then we must have an arrow from U1 to V. Okay? And then we check whether we can whether we have an arrow from V to U2. Because if we have an arrow from U1 to V, and now we have an arrow from V to U2, then we can insert V between U1 and U2. Okay, we remove the edge from U1 to U2 and we replace it with an edge that goes from U1 to V and then from V to U2. Okay? If this is not possible, if there is no arrow between V going from V to U2, then we must have an arrow that goes from U2 to V because this graph is a tournament. And then we try to insert the vertex between U2 and U3. This will be possible if we have an arrow from V to U3. If we do not have an arrow from V to U3, then we have an arrow from U3 to V, and we try to insert the vertex between B3 and B4. Okay, between U3 and U4, and so forth. Okay. In the final situation, if we do not find any place in the middle to insert the vertex, this is because all the arrows point from U1 to V, from U2 to V, from U3 to V, and so on. So in that case, we also have an arrow from the last vertex to V, and we can insert V at the end. Okay? If the graph is a tournament, then it is guaranteed that at least we are going to be able to insert the vertex at the very end of the graph. Okay? So what we do, let me repeat once again, is that we write the vertices in a given order, the one that you want, and then we select the first vertex, the next vertex from that order, from that list, and we try to insert it in the path. Okay? If we can, we insert it at the beginning. If not, we try to insert it in the middle, and if not, we know that we will be able to insert it at the end. We repeat this with all the vertices in the initial list, and when we process the last vertex, then we have a Hamiltonian path. Okay, so this is the algorithm to find a Hamiltonian path in a tournament. Okay, so this is something that we can do if we are given a graph that is a tournament. If you are given a different graph, then in general this algorithm is not guaranteed to succeed. It may find a Hamiltonian path in some graphs, but in others it will not succeed. And if it does not find a Hamiltonian path, it does not mean that the graph has no Hamiltonian paths. It only works in general for tournaments. Okay, so if you are given a graph, if it is a tournament, you can use this algorithm. If it is not a tournament, then there is some things that you can do. As I've mentioned before, you can try to enumerate all the possible paths. That is very time consuming, but it can work for small graphs. And if not, you can try to somehow find the graph by the Hamiltonian path by inspection. Okay, if I give you an exercise with a graph and I ask you to find the Hamiltonian path, it means that if it is either a tournament or it is easy to find the path or to show that no path exists. Okay, so for instance, imagine that I give you a graph like this one. Okay, something like this. So this is clearly not a tournament, but is easy to find a Hamiltonian path here. You can do something like this. Okay? So if I give you a graph in an exam and I ask you to find a Hamiltonian path or to show that there is no such a path, then it is either a tournament and then you can use the algorithm, or is something like this in which is easy to find the Hamiltonian path, or is something like this. Imagine something like this. Uh, Let me add something like this here. Okay, so it's something like this, in which it's easy to show that there is no Hamiltonian path, because when you get to this vertex, then you can go either to this part of the graph or to this other part of the graph. But it's not possible to go from one to the other. So once that you reach vertex A, you can go to one part or to the other, but you cannot go to both. Okay, so you cannot use all the different vertices in the graph. Okay, so if I give you a problem with a graph to find a Hamiltonian path or to show that there is no Hamiltonian path, it will either be a tournament or it will be easy to find the path or to show that not such a path exists. Okay, so let's do an example of a graph of a tournament and how to apply the the algorithm that we have just studied. So let me first draw a tournament. Remember that a tournament is a complete graph in which we give direction to all the arrows. So let's say that this arrow goes in this direction, this arrow goes in this direction, this one in this direction, this other one in this direction, this other one in this direction, this one like this one like that, and this one like that. Okay, so this is a tournament, and we have these 5 vertices. Let me give them names, and we want to find oh, there is a missing arrow here from 5 to 3, for instance, and from 4 to 2, for instance. Okay, now this is a tournament. Let me check. We have 4 arrows in each of the vertices. Okay, so now it is a tournament. Okay, and we want to find a Hamiltonian path in this tournament. So what we do is to first write all the vertices in an order. For instance, 1, 2, 3, 4, 5. Okay, but it can be any order that you want. And now we insert the vertices in the path that we are going to create in the first position that is possible. So we start with 1. Since there are no vertices yet, we can only insert it in the beginning. Okay, there are no restrictions here, so we insert it in the beginning. Now we try to insert 2, and we check whether we can go from 2 to 1. If we can go from 2 to 1, then we insert the vertex at the beginning. In this case, we cannot go from 2 to 1, but we can go from 1 to 2, and then we insert 2 after 1. Okay, now we try to see if we can insert 3 before 3 is the next element in the list, 3 before the first vertex here in the path that we are creating. And since we have an arrow from 3 to 1, we can do that. we can go from 3 to 1 and then to 2. Now we try to insert 4. And we check whether we can insert 4 before 3. For that, we would need an arrow that goes from 4 to 3, but the arrow goes in the other direction. It goes from 3 to 4. So we try to insert it between 3 and 1. For that, we would need an arrow. Okay, so we have an arrow that goes from 3 to 4, and we would need an arrow from 4 to 1. Okay, but the arrow does not go from 4 to 1, so we cannot do that. We now try to insert the vertex between 1 and 2. And since we have an arrow that goes from 4 to 2, we can do that. So in this case, the next step is to have this path that goes from 3 to 1 to 4 and then to 2. Finally, we are going to insert the last vertex, which is 5. And what we do is to try to insert 5 before 3. And that, in this case, is possible. So we get 5 to 3, and then to 1, to 4, and to 2. Okay? And you can check that this is indeed a Hamiltonian path in the graph. So we can go from 5 to 3, then to 1, then to 4, and finally to 2. This is a Hamiltonian path in this graph. Okay? Let's do another application of this algorithm, but with a different order. So I'm going to delete all this, and I'm going to choose a different order. Okay? So for instance, I'm going to choose the inverse order. I'm going to choose 5, 4, 3, 2, 1. Okay, so at the very beginning I insert the 5. Now I try to insert the 4 before the 5, and I can do it because I have that arrow in the graph. Now I try to go from 3 to 4, I can do it. Okay, and then to 5. Now from 2 to 3, I can do that. And then from 1 to 2. So in this situation, I was able to insert the vertex all the time at the beginning of the path. Okay, but in general, it doesn't need to happen. Okay, let's try with a different order, with another order yet. So, for instance, I don't know, 1, 3, 5, 2, 4. Oh, 1, 3, 5, 2, 4. Okay, so I insert 1, then from 3 I can go to 1. With 5 I can go to 3, and then to 1. From 2 I cannot go to 5, but from 5 I can go to 2, and then from 2 I can go to 3. So I insert it between 5 and 3. And finally, the 4 can go before the 5. Okay? So you see that with different choices of the order of the initial list of vertices, maybe I find different Hamiltonian paths. So one of the paths that we found was 1, 2, 3, 4, 5. And this is different from this path here, which is 4, 5, 2, 3, 1. Okay, but independently of my choice of initial order of vertices, if the graph that I have is a tournament, I will find a Hamiltonian path. Maybe a different path with a different order, as in this case, or maybe the same path with two orders. It depends, but I will always find a path in the graph, a Hamiltonian path in the graph. Okay, so as a quick summary of what we have studied today, we have this problem of finding paths that use all the vertices in the graph once and only once. This may seem similar to the problem of finding paths that use all the edges once and only once, but this problem is much more difficult. Okay, this problem is NP complete, meaning that it's easy to check, but we do not know of any algorithm that can solve the problem quickly, that can find a solution quickly. Okay, and in fact we strongly suspect that there is no such an algorithm, because if we could solve this problem quickly, we could solve many other problems quickly, and P would be equal to MP, which is something that we don't believe it's true, although we cannot yet prove it. Okay, but we can use special algorithms to solve this problem quickly if we restrict ourselves to special situations, to special types of graphs. For instance, if we restrict ourselves to to tournaments, to graphs that are directed and complete. Okay, and we have studied this algorithm that first chooses an order for the vertices and then inserts these vertices into a Hamiltonian path in the first position possible. Okay, and since we always have an arrow either from the vertex to one of the vertex in the path or in the other direction, then it is guaranteed that we are going to succeed. Although maybe we obtain different Hamiltonian paths with different orders. Okay, so this is all for today. As always, if you have any question, please use the discussion forum or email me. And remember that you need to turn in your exercise for Unit 2 on Monday, on April the 20th. Okay? Uh, if you have any question about that, also please feel free to email me. Thank you for your attention, and I will upload the new lecture for Monday soon. Okay? Bye.